Hi everybody, happy Monday. This is March 30th, lecture 27. We're discussing section 8.7, which is about Taylor and Maclaurin series. Our first day on this topic. We'll discuss it again in lecture on Wednesday, and you'll have problems about this in recitation tomorrow. All right. So in section 8.5 and 8.6, we discussed series and power series. So we discussed in section 8.5 things like this. We have a bunch of terms added together. So that's A0 plus A1 plus A2 and so forth. In section 8.6, we had power series. So series of this form, sum from 0 to infinity of Cn x to the n. Well, x minus a to the n. So this is a power series centered at a. And so the way that looks is C0 plus C1 times x minus a plus C2 x minus a squared plus and so forth. And then in section 8.6, we discussed the idea that a power series that we build like this may or may not converge. So the limit of the partial sums may or may not exist. So we discussed that if, there's a big if there, if the power series converges, we can think of it as a function of x. So if the power series converges, we can think of it as a function of x. So we have a function that behaves this way. Now, continuing on the idea of this, in that case, where the series does converge, then there's a relationship between the coefficients and the derivatives of f. So that the relationship is between Cn and the nth derivative of f. So that nth coefficient is this. You take the nth derivative of f, and you substitute in x equals a, and you divide by n factorial. That comes from just looking at, for instance, what if we don't take a derivative at all? So the 0th derivative of this series would be this series, and you plug in x equals a, all these terms get killed. And so when I look at the 0th derivative of this thing at x equals a, what ends up dropping out is that coefficient. If I take the first derivative of this thing, then that gets killed. And then I have the derivative of the first derivative of this is just going to be c1. And then the derivatives of all these terms are going to have x minus a's in them. So if I take the first derivative and I plug in x equals a, all those terms get killed. This term already got killed, and what we have surviving is just c1. So this is just sort of easy examination of what happens to this series when you take these derivatives. So again, in section 8.6, we had series that converges, and that gave rise to a function, f of x. So this is kind of subtle. There's a lot of subtle, in this part of the book, there's a lot of really hard math, and there's also a lot of really subtle stuff that's not hard computationally. So in section 8.7, we want to turn this around. We want to ask this question. I'll come over here to this sideboard. We want to ask this question. Given a function f of x, is there a series that represents that function? So the power series would have to look like this. So is there such a thing that represents that function? So notice, so again, this is subtle. If you're not confused, it means you're not paying attention, because this is confusing. If the answer is yes, if there is a power series that works, then we know how it's going to have to behave. Its coefficients are going to have to look like that thing over there on the front board. So if there is a series that works, its coefficients will have to behave this way. So the nth coefficient is going to be the nth derivative of the function evaluated at a divided by n factorial. So given a function, we can just build the series this way. So the series Cn x minus a to the n, the sum from 0 to infinity, where each of the coefficients behaves this way. And this series is called the Taylor series. for f of x at x equals a. That's that thing. Now, if in the special case where we have the number a being the number 0, we get what's called the Maclaurin series. For f of x. And this is just the Taylor series at x equals 0. At a equals 0. Yeah. So we can build this Taylor series for f of x at x equals a, and then we can just build the Maclaurin series for f of x. But that does not address the question of, does this series actually represent our function? Remember, a while ago when I started this, I had this, talked about what we did in section 8.6. We can talk about a series, and if the series converges, it represents a function. We can call that function f. That function came from the series that converges. The series that converges first. It defines some function which we can call f of x. Now, go back to the sideboard. Sorry, Gabriel, I keep going back and forth. Well, what if we start with a function and we build this series? Well, okay, we can build it, and maybe this series converges to some function, but we're not really sure that that function is our function. That's a hard question. So a much harder thing is to determine whether the Taylor series that we built really does represent f of x. Again, maybe this series converges, but maybe it converges to something else, not our function. So whether it really equals our function f of x. Now, this harder question is really as hard as anything in our course. And your homework does not actually include questions where you have to, I don't think, where you have to address this much harder question. So this much harder question is addressed in the chapter, but I'm going to punt because I discussed it last class meeting, and it's just a good way to put a whole class of students to sleep. So I mean, I could close the shades and it would be even more effective. So what we're going to talk about in class today is building these Taylor series and Maclaurin series, and I'm going to refer you to the book for some of the examples where they show that the series really does represent what we want it to represent. They're cool questions, but it's lots of details, lots of messy details, and it's the kind of thing that does not work well in a lecture. So meeting part 2 is examples. So example 1. Find the Maclaurin series for f of x equals e to the x. So again, here we start with a function, and the question is, can we come up with a series that represents it? Well, we have to build those coefficients. The coefficients are c subscript n, which is the nth derivative, so that's represented this way. That means the nth derivative of x at x equals 0 over n factorial. So that means that I'm going to find the nth derivative of e to the x, and then I'm going to substitute in x equals 0, and then I'm going to divide by n factorial. Well, when you start taking derivative of e to the x, what do you get? What's the first derivative of e to the x? Now remember, if I call on you, then I'm not going to call on you again. So you might want to save your questions, your answers for ones that are more challenging. If this is an easy question, I should have like a whole room full of hands. What's the first? Actually, there are like 20 of you. I'd like 20 hands in the air. What's the first derivative of e to the x? Mary. E to the x. What's the second derivative? E to the x. So every derivative is just e to the x. So we have here e to the x, that's our derivative, and we're going to substitute in x equals 0, and we're going to divide by n factorial. Oh, so what is e to the x evaluated at x equals 0? Cassie? 1. So I get 1 over n factorial. So that's my Cn. So that means that the series is, or the Maclaurin series, is this thing. Sum as n goes from 0 to infinity of 1 over n factorial times x to the n. So that would be x to the 0 over 0 factorial plus x to the 1 over 1 factorial plus x squared over 2 factorial and so forth. Remember, the 0 factorial is just the number 1, so this is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. That's the easy part. Finding the Maclaurin series. So the question is, so this is the hard question. Does this series really represent e to the x? So does this series really equal e to the x? So again, there's the idea, we have a series, and actually from previous techniques, we prove that the radius of convergence of this series is infinite. So this series converges for all x. So in fact, this series does represent some function. But is that our function? Is it the function that we wanted it to represent? So the answer is yes. So we can write that e to the x is equal to its power series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so forth. So that's our first Maclaurin series. Remember, Maclaurin series is just a Taylor series where a is the number 0. Okay, example 2. Find the Maclaurin series for f of x equals sine of x. Okay, well, again, we need to build the coefficients. So we need to find the coefficients. So I'm going to make a table. N, and then we're going to need to find the nth derivative of sine of x. And then we're going to need to evaluate that at x equals 0. And then finally, we're going to need to build the coefficient, which is Cn, which is that thing. So the nth derivative of sine of x. And then we substitute in x equals 0, and we divide by n factorial. All right, so here we go. When n equals 0, that means that I don't take any derivatives, so I just have sine of x. So when I plug in 0, I get sine 0. I just get the number 0. So C0 is going to be 0 over 0 factorial. So that's 0 over 1, because remember, 0 factorial is 1. So that's the number 0. When n is 1, I get cos x I take one derivative, I get cos x. So cos 0 is 1. So C1 is going to be 1 over 1 factorial, so that's the number 1. When n is 2, I take the second derivative, so I take the derivative of cos, and I get minus sine of x. When I plug in 0, I get minus sine of 0, so that's 0. And so C2 is 0 over 2 factorial, so the number is 0. All right, let's keep going. When n is 3, I get the derivative of this. That gives me minus cos x. So when I plug in 0, I get minus cos 0. So that's minus 1. So C3 is going to be minus 1 over 3 factorial. Now that's not hard to compute. 3 factorial is just 3 times 2, which is 6. But I'm going to leave it in that form. Let's keep going. When n is 4, I take the derivative again. So I have 4 derivatives. That means I take the derivative of this, and I get sine of x. Oh, well, I've come back to where I started. I'm going to have 0, and I'm going to have 0 over 4 factorial. So from here on, this pattern repeats. And this pattern repeats. 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so forth. So my series is it's going to look like this. I'm going to have 0, x to the 0, plus 1, x to the 1, minus 1 over, plus 0x squared, minus 1 over x over 3 factorial, x cubed. I'm going to write out a couple more terms just so we get this pattern. So I have going to have 0x to the fourths, and then I'm going to have a plus 1 over 5 factorial x to the fifth, and so forth. So how can we write this more concisely without having to have all those terms? Well, let's just leave out the 0 term. So we're going to have 1 x to the 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth. And let's write this with the signs obtained by some kind of formula. So this is minus 1 to the 0 times x to the 1 plus a minus 1 to the 1 power over 3 factorial x cubed plus a minus 1 squared over 5 factorial x to the 5th, and so forth. The reason I want to do that is I want to have a formula for these coefficients. Well, I can write this as a sum starting with the index m as in maraschino. So m equals 0 to infinity. I'm going to have minus 1 to the m power. And then what about my exponents for x, and what about my numbers for the factorial? Those are the odd integers. So I can get those numbers by doing 2m plus 1. So 2 times 0 plus 1 is going to be 1. 2 times 1 plus 1 is going to be 3. 2 times 2 plus 1 is going to be the number 5, and so forth. And then on the bottom, 2m plus 1 factorial. So this is our Maclaurin series for sine of x. So again, we have this hard question. I can build this thing, but does it really work? Does this really represent sine of x? From section 8.6 techniques, we actually can figure out that this thing does converge. This thing does define a function, but we don't know if it's our function. So that, again, is that difficult question, and it's addressed in the book. So the question is, does this series really represent, does it really equal sine of x? And so the answer is, again, see the book. Is yes, it does. So we can say that sine of x equals this series, the sum as m goes from 0 to infinity of minus 1 to the m, x to the 2m plus 1 divided by 2m plus 1 factorial. So that's 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so forth, minus x to the 7th over 7 factorial. It keeps repeating. That's our second example. And the question about convergence, remember from section 8.6, there's a question of does the series converge, and for which x's does it converge? For both of these series, this is true. This series does represent e to the x, and the radius of convergence is infinite. This is true for all x. And over there, this formula for sine of x equals this. This is true for all x. All right. Now, example 3. Find the Maclaurin series for f of x equals cos x. So here we actually have we have two solution methods. Solution method 1 is we go through something like we did over there for sine of x. We build all the coefficients. So the result is we get this. Cos x equals, I didn't actually write this down. Let me make sure that I get this right. It's 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial and so forth. And what that is the sum as n goes from 0 to infinity. I'm going to use m as in Mary or as in maraschino. Minus 1 to the m over x to the 2n over 2n factorial. There should be 2n in parentheses, factorial. So that's everything just like what we just did, including the fact that this series does converge and it does actually equal cos x. So you can see the book for that solution. Can anybody think of what another method would be? Raise your hand. What's another way of building the Maclaurin series for cos x? Well, use previous results. Well, we've only got 2 previous results. Which previous result might be handy?
Sine of x.
Yeah. So we know that cos x is equal to the derivative of sine of x. Okay, now, just leave the derivative chilling out there. This is d dx of that thing over there. So here we've used example 2. Now, what can we do here? I've got an infinite series, and I've got a derivative parked out in front of it. Marcy?
We remove the first index from the sequence?
No, something more fundamental than that. Annika?
Remove the derivative symbol inside the summation.
Yeah, that's the big thing. Remember, this involves a limit, this involves a limit, and it's a big fact from the previous section that I can change the order of those limits. So I do d dx of those terms. That's huge. Now notice in that derivative, the minus 1 to the m power doesn't involve x, so I can pull that through. And also the 1 over 2m plus 1 quantity factorial, that doesn't involve x either. So I have this series, sum as m goes from 0 to infinity of minus 1 to the m over 2m plus 1 factorial And then I have to take the derivative of x to the 2m plus 1. All right, so what is that derivative? What is this derivative? Liam, you're the closest to having your hand up.
Is it 2 times the natural or the value to be L and A?
No, just taking the derivative of this power series, I mean, this power function. How do you take the derivative of that power function? X to the 2m plus 1. Yeah, exactly. So this is going to be the sum as m goes from 0 to infinity, minus 1 to the m on top. And on the bottom, I've got 2m plus 1 factorial. And when I take the derivative of that, I bring down the exponent, 2m plus 1, and then I lower the exponent by 1. All right. Can anybody think of how to simplify this expression?
You can cancel out the 2m plus 1 in the numerator and reduce the factorial to just 2m.
Exactly. Wonderful. So this is going to be the sum from 0 to infinity, minus 1 to the m survives. But this, remember, this is a product of a whole bunch of terms, beginning with 2m plus 1, and then 2m, and then 2m minus 1, all the way down to 2, and then down to 1. When I have a 2m plus 1 on top, that kills that first term, or it cancels it. So what I end up with is 2m quantity factorial times, and then what's on top, I have x to the 2m. Same thing, same result. Isn't that cool? So if you go through all the stuff of building those coefficients using the formula for building coefficients, you get this series. Or if you use our previous technique of finding a derivative term-wise, you get the same result. Same result as other method. Allison, Ethan is not here. Gracie, Kenzie. Okay. Example 4, find the Maclaurin series for f of x equals sine pi x. Well, we have the same option. We could build all the coefficients because this is section 8.7, and that's the kind of thing we do in section 8.7. Method 2 would be to use the previous results. So sine of pi x would be, well, let's go back over there and get that series for sine of x. We'd have the sum as m goes from 0 to infinity of minus 1 to the m. And then we have x, instead of x to the 2m plus 1, we'd have pi x to the 2m plus 1. So we use, and then divided by 2m plus 1 factorial. So we use, again, example 2. So in the book, you are assigned a problem like this. And I think what they have in mind is you're going to go through all the grunge work of building those coefficients. It's not that hard. These series involving sine and cosine, they repeat pretty soon. But you see what you're going to get you're going to get the exact same thing, except there's going to be a factor of pi raised to the 2x to the 2m plus 1. So the sum, as m goes from 0 to infinity, of minus 1 to the m pi to the 2m plus 1 over 2m plus 1 factorial, and then written as x to the 2m plus 1. Now you might think, why separate these? This is actually more complicated looking than this. But the thing is, when you present a power series, it's supposed to be a sum of a bunch of coefficients times powers of x. You're not supposed to have anything in there with the x. So that's example 4. Example 5. Find the Maclaurin series for f of x equals 1 over 1 minus x quantity squared. Okay, well, as you might guess from the way I've been doing these, this is going to be one where we can do two methods. Method 1 is to build the coefficients. So now remember, this is 1 minus x raised to the minus 2 power. So let's build our coefficients. So we have n, then we have the nth derivative of 1 minus x to the minus 2 power. And then we need to have the nth derivative, and this should say, let me see. And then I need to have the nth derivative of that thing evaluated at x equals 0. And then finally I need to build my coefficient. Cn is going to be that thing, the nth derivative evaluated at x equals 0, and then divided by n factorial. Okay, here we go. When n is 0, I don't take any derivatives, so I just get 1 minus x to the minus 2, so that's 1 over 1 minus x squared. When I plug in 0, I get 1. 1 over 1 minus 0 squared, I get 1. So C0 is going to be 1 over 0 factorial, so that's 1 over 1, so it's just the number 1. When n is 1, I take the derivative of that, and I get minus 2 times x times 1 minus x to the minus 3. So I do the derivative of the outer function, but then I got to take the derivative of the inner function as well. Chain rule. So I get 1 minus x to the minus 3rd power. So in other words, 1 over 1 minus x cubed. And when I substitute in x equals 0, I get the number 1. Wow, that's weird. Let's do the second derivative. Oh, I'm sorry. This is bad. This should be 2, 2, 2. And so the coefficient is going to be C1 is going to be 2 over 1 factorial, so the number 2. let's find the second derivative. Well, let's see. I take the second derivative of this, and I bring down the exponent, so I get minus 3 times 2. And then I have 1 minus x to the minus 4th power. But I have a chain rule problem. I've got to multiply by the derivative of the inner function. So I end up with 3 times 2. So in other words, 3 factorial times 1 minus x to the minus 4th power. So 3 times 2 over 1 minus x to the 4th. So when I plug in x equals 0, I get 3 times 2. And so my second coefficient is 3 times 2 over 2 factorial. Oh, wait a second. So that's 3 factorial over 2 factorial. That's just the number 3. Wow, that's pretty cool. That's very simple. Let's just do one more of these things to see if we're onto something. So when I do C3, I take the derivative of again, so I get the derivative of this is going to be minus 4 times 3 times 2 times 1 minus x to the negative 5th times a minus 1. And so that's going to be, let's just skip to it. I'm going to have 4 factorial over 1 minus x to the 4th. When I plug in x equals 0, I get just 4 factorial. So what's my C3 then is going to be that number, 4 factorial, divided by 3 factorial. So it's just the number 4. So we get the idea that the nth coefficient is just n plus 1. I have like 1 minute to wrap this up. So the Maclaurin series is the sum as n goes from 0 to infinity of Cn x to the n, but that's just the sum as n goes from 0 to infinity of n plus 1 times x to the n. So that's going to be 1 times x to the 0 plus 2 times x to the 1 plus 3x squared plus and so forth. Anybody know what method 2 is? Well, let's go back to our original function. F of x is 1 minus x, 1 over 1 minus x squared. But recognize that that's the derivative of 1 over 1 minus x. Because if you take the derivative of this, you can use the chain rule and so forth, you get that. Remember that we have a geometric series result for this. This is the derivative of 1 plus x squared plus x cubed and so forth. So this is the geometric series. This is from section 8.6. So the derivative of 1 is 0. The derivative of x is 1. So I get 1 plus 2x plus 3x squared plus 4x cubed and so forth. You see, it's the same result. It's pretty cool. Now the question is, when does this really represent? Here the question is very interesting. What's the domain of this function? Remember, the domain of this function is all x's except 1. What's the domain of this power series? This power series had an r of 1. It only converges when x is between -1 and 1. Its derivative only converges between x equals -1 and 1. So this Maclaurin series does equal our function, but only for those x values. It turns out there's a bit of work to confirm. We know that this series converges for those x values. That's a bit of work, and also showing that it really does represent our function on that interval is a bit of work. But actually now we actually know that because, yeah. All right, so that's a good place to stop. Thank you, everybody. See you tomorrow in recitation.